Welcome to my class. By now we already have the understanding of logic gates, and we know NAND and NOR. These two logic gates are called universal logic gates because by using NAND or NOR we can implement all other logic gates. In today's class we will implement all other logic gates by using NAND gate, and in our following class we will implement all other logic gates by using NOR gate. So let's get started. First, we will implement the simplest gate, NOT gate, by using NAND gate. By now, we already have the understanding of the symbols of all the basic gates. Now, this is a symbol of NAND gate, or rather we can say this is a symbol of two input NAND gate. Now here, as we can see, both the inputs are sorted. So if we apply input A here, so this is our boolean variable. Now since these two inputs are sorted, so second input of this two input NAND gate will be also A. Now we know that if A and B, these two are inputs of a NAND gate, then this is the output of a NAND gate. In our case, both the inputs are A, so it will be first AND operation between A, and then complement of that. So that completes the output of NAND operation. So when A and A, we have the AND operation between two same inputs, then it will be finally A only. And since we have the complement, so it will be finally complement of A, which is the NOT operation of the boolean variable A. Next, we will implement AND gate by using NAND gate. Now this is the circuit, and now we will see how it is possible. So as we can see, we have two input NAND gates. So in the first two input NAND gate, if we suppose apply A and B, these two inputs, then as per the operation of NAND gate, the output of this first stage NAND gate will be AB bar or AB complement. Now what we can see in the second stage, or in case of second two input NAND gate, both the inputs are shorted. That means at both the input side we will be applying AB bar. This will be our input in this case. So first input will be AB complement and the second input will be AB complement. Now what will be the output? This is NAND operation, so it will be AB complement. This itself is one input, and then another input is AB complement, as we can see, and then between these two inputs, first we will have AND operation and then we will have complement of that, and that completes the NAND operation. So AND plus NOT. Now AB complement, if that is taken as a single input and we are doing AND operation between two same inputs, as we can see in the previous example, that it will be finally AB complement only. So one variable will vanish, and then we have this whole complement, so we will have the second complement on that. And we know when we have double complements, then they will cancel each other, so it will be finally A B only. So we can think this way, that if suppose the value of one boolean variable is 0, then complement of 0 is what? We know 1. Now if we take complement of 1 is what? It is 0. That means we are getting back the original value, which was 0. So that means double complement means the original values. So this is how we implement AND by using NAND. Next we will implement OR gate by using NAND gate. Now here, as we can see, we are using 3 2 input NAND gate, and now in the first NAND gate, what we will do, we will take one boolean variable that will be our one of the inputs, because finally this we will be implementing two input OR gate. So there we will be having only two inputs, and if those two inputs are A and B, so in our whole circuit we will be having only two variables, and by those two variables we have to implement. So what we have done here is, in the first NAND gate we have shorted both the inputs of that NAND gate, and in the second NAND gate also we are taking the second variable v and we have shorted both the inputs. So this way what will happen, we have seen the NOT operation already, since both the inputs are same, and that is a for the first NAND gate. So here the output will be a complement or a bar, and for the second NAND gate the output will be b complement. Now here a complement and b complement, and again third two input NAND gate that has inputs like a complement and b complement. So finally the output of this third NAND gate will be a complement itself is one input, and then b complement is another input. So first we will perform AND between these two inputs, and then we will perform NOT, then that will complete NAND operation, and plus NOT. So this way what will happen, we will apply the De Morgan's law. So a complement and b complement, that will give us a plus b whole complement, and then we already have another complement, the whole complement, so that we need to consider. So this way what will happen, when the output of this whole circuit we have double complements, and double complements means they will cancel each other. So finally what will remain, a plus b will remain as output of this whole circuits, and a plus b means OR operation between a and b. Now next we will implement NOR gate by using NAND gate. So OR we have already done, and then that will be followed by a NOT gate. So this will be the circuit. So this much, till this much we have already implemented, we already know the logic. So here a will be taken as one input, b will be taken as the second input. So a, and in the first NAND gate, two input NAND gate, definitely the inputs are shorted. So here it will be a complement, here it will be b complement, and in the third NAND gate the inputs are a complement and b complement, and we have already seen the output of this NAND gate is a plus b. And now what we are doing, a plus b will be taken as one input for the fourth NAND gate, and again that will be taken as the second input. So what will be then operation, it will be a plus b will be one input, and then the second input will be again a plus b. So a plus b itself is one input for the fourth NAND gate. Then between them we will perform AND operation first, and then that will be followed by NOT operation. So that way it will complete the NAND operation. Now a plus b and again a plus b, between them we are performing AND operation. So it will be finally a plus b only, and then we have this complement. So it will be a plus b complement, and that is what? That is NOR operation, two input NOR gate. Next we will implement XOR gate or XOR gate by using NAND gate, and this is the circuit diagram. So here what I can see is we have implemented XOR gate by using four two input NAND gate. So we can implement in other ways also, but our aim will be always to use minimum number of gates, definitely. So minimum number of NAND gates, two input NAND gates, that we need is 4 to implement two input XOR gate. So again what we can see here is, in first two input NAND gate we will be taking both the variables a, b, and the output of the first two input NAND gate will be ab bar or ab complement. And for the second two input NAND gate, what are the inputs? The one of the inputs is what? It is a. So here it will be a, and the second input is ab bar or ab complement. And for the third NAND gate, the first input is, or one of the inputs is b, and again the second input is ab complement. And then we have to see that what will be the outputs of the second and third NAND gate. So it will be first AND operation between a and ab complement, and then NAND, so whole complement. And for the third NAND gate it will be AND operation between b and ab complement first, and then we will perform NOT, so that will be the NAND out. Then what we are doing is we are using fourth NAND gate, two input NAND gate, and we are using these two as inputs of the fourth NAND gate, and then we will see that the output of this fourth NAND gate will be nothing but the output of 2-input XOR gate. But before that, we need to simplify a little bit, then only it will be clear. So what we are doing here, we are performing again NAND operation. So in this case, our inputs are, so A and AB complement, and then whole complement is our one input and then second input. And then what we are doing, first we are performing AND operation and then we are performing NOT operation. And here, to simplify this expression, we will use De Morgan's laws. So what we can see here is AB bar. So AB bar can be written as A bar plus B bar as per De Morgan's law, and similarly in the second term also that has been written. Now what I will do, we will perform AND operation between A and this term. So A and A bar, that will give us what? As per Boolean algebra, we know that will give us 0, and A, and then what remains is A and B bar. So here we will be writing A B bar, and then we have another bar or another complement here. So this is one term, and from the second term again B and then A bar. So B A bar or A complement plus B and B complement, that will give us 0. So this will be our second term, and then between these two terms we will have and then followed by NOT. Now what we can see here is we have this variable A B bar. A B bar, suppose if we consider that as M, another variable, Boolean variable, and B A bar, that if we consider as another Boolean variable N, then this is the format: M bar and then N bar and then whole bar. So M bar and N bar, as per De Morgan's law, we can write as M plus N and then whole bar, and already we have this second complement, so we will have double complement on this operation M plus N or M or N. So double complements means they will cancel each other, so what will remain is M plus N. And what is our M and N? It is A B complement plus B A complement, and that is what? That is the output of 2-input XOR gate. So that means when we are performing this NAND operation between these two inputs, finally the output will be A B complement plus B A complement. So this is how we will implement 2-input XOR gate by using 2-input NAND gates, and this time we will need 4 NAND gates. Next we will implement XNOR gate by using NAND gate. Since we have already implemented XOR gate, so we will need one more NAND gate to implement XNOR gate. And as we have seen for OR and NOR, this is also same. So till this much we already know, we have just now seen. So this will be A, this will be B. So here it will be AB complement, it will be A, and it will be AB complement, it will be AB complement, it will be B. And now we are performing the NAND operation between, here the output will be A and AB complement first and then NOT, and here the output will be for the third NAND gate, it will be B and then AND AB complement and then whole complement. And output of this NAND gate, we know that is the output of XOR gate that we have seen. This is the implementation of NOT gate by using NAND gate. So when XOR will pass through our NOT gate, this will become XNOR gate. So this is how we can implement XNOR gate or 2-input XNOR gate by using 2-input NAND gate, and this time we need 5 2-input NAND gates. So this class was all about implementation of all other logic gates by using universal gate like NAND gate. In our next class, we will be learning the implementation of all other gates by using another universal gate, which is NOR gate. So this is the end of today's class. Thank you.